This is a 72 LED inspection light, aka worklight, camplight, goes by many names and different brands. This is a Larson branded one that I picked up around 10 years ago at Robert Dias. And since then the rubberized exterior has gotten a bit tacky. The hook is broken. And rather than throw it out, I had a quick look inside and found there was a lot of empty space that I could put electronics in. So I've modified this so that it now functions as an 8-bit binary counter. Also added a hot snotted button to the outside to change modes. This is a simple pulsing heartbeat-like flash, and of course a Larson scanner. So let's take a look inside to see how this hack was done. Internals of the modified worklight. Originally, the 72 LEDs were arranged in 3 rows, each a row of 24 LEDs. Was powered by these parallel strips, copper strips. But as you can see, I've cut through the negative strips about every 3 columns. Soldered these bridging wires. This wasn't part of the original worklight, so these had to be soldered on to connect a 3x3 block of LEDs together. And you have 8 of these blocks all along the entire length of the worklight. The current driving each block of 9 LEDs is sunk to ground via these 2N3904 NPN transistors. The base pins of the transistors are driven by a 74HC595 shift register via these 1 kilo ohm resistors. And the contents of the shift register are controlled by an ATTiny 85, an 8-pin microcontroller. This can be programmed via the Arduino IDE, but requires removing the ATTiny from this 8-pin build socket, as there is no ICSP or in-circuit system programming. So this 8-pin microcontroller, it has 5 general purpose input-output pins. Pins 0 to 3 are what is controlling the shift register, whereas general purpose pin 4 is the input to a button, the hot snotted button on the outside of the case, where these wires lead to, and that allows us to select the various different effects. Now the general purpose pins 0 and 1 have built-in pulse width modulation, so I think I connected one of them to the output enable of the shift register to allow us to program various fading effects. The 74HC595 shift register is unable to supply sufficient current to drive the 72 LEDs, where you have 9 LEDs per output being controlled by each of the 8 outputs of the shift register. Hence, that is why the power is actually driven, well, sunk through these transistors, which incidentally date back to the 70s. These were originally bought from Radio Shack. Yeah, I did this mod mainly as a way to test out whether these ancient transistors were still any good. This is the original packaging in which they came in, and the pins were very tarnished. Had to do a lot of sandpapering to expose the metal underneath so that it could take solder. The current passing through the LEDs is limited via these resistors that were already part of the worklight circuit. However, in cutting the copper traces, I've bypassed some other surface mount resistors. Let's see, so these surface mount resistors got bypassed. They're no longer part of the worklight circuit. They seem to be about 10 ohms. The microcontroller is powered more or less directly by the worklight batteries themselves, which are 4 AA nickel metal hydride rechargeables. As there's no regulator, I cannot actually use alkaline batteries, as this would take the supply voltage to above 6 volts, which is too much for the ATTiny 85. Initially, I tried this modified worklight without any decoupling capacitors. However, I found that switching between modes would sometimes result in the circuit glitching and locking up, and then it won't respond to anything. The flashing LEDs being on the same power supply probably made the microcontroller supply too unstable for it to function properly. So I added this 47 microfarad electrolytic cap, as well as a 100 nanofarad ceramic that you can't quite see. It's underneath this board, but it's actually very close to the microcontroller in that it's connected directly to the ground and voltage in pins. And now it doesn't glitch anymore whenever I switch between the various flashing modes. When you first turn on this hacked worklight, the first flashing mode is the 8-bit binary counter, considered to be the hello world of shift register programming. Push the button for the next mode, it goes into the heartbeat animation. Now this demonstrates the use of the built-in pulse width modulation of the GP pins of the ATTiny 85. So one of the pulse width modulation pins is connected to the output enable, which allows you to program various fading effects. In the third mode, now the Larson scanner, aka Knight Rider or Cylon Eye, this uses software pulse width modulation. And what you're seeing here is actually 3 patterns being shifted and shown in quick succession. One has one of the block of LEDs fully lit. Another one has that block and the one just behind it fully lit. And the third pattern has that block, the one behind it, and the one behind that. 3 blocks fully lit. And cycling over that over and over and over, so that you can see a bright block followed by a less bright block followed by one that is dimmer than the first 2. Let's measure the current draw. Of course, the binary counting mode, the current draw will actually depend on how many of the LED blocks are actually lit up. So it's approaching maximum. And then it drops back down to 0 again. So the pulsing heartbeat mode, it goes from 0 illumination to full illumination. On Larson scanner, since it's just oscillating through the same 3 patterns, just shifted along, I don't expect the current to change that much. The worklights I've bought more recently that I tend to use now come in these slimmer packages. It's because the LEDs are all chip on board type. However, it might still be worth picking up one of the bulkier worklights, simply because they have greater potential for modding and their ease of hackability.